Hi there, folks. In this video, we're going to be looking at flux, the concept of flux, which is not just about electricity, but then we are going to look at that as regarding Gauss's law, helping us understanding the electric field. This is our third and final method for finding the electric field. We had the first method, which worked for point charges or shells or that kind of stuff, using Coulomb's law and discrete particles. Then we used sort of an integrated version of Coulomb's law for line segments, arcs, rings, disks, things like that. And then in this video, we're going to talk about Gauss's law, which uses a surface integral, or at least sets one up to help us think about these things. So Gauss's law makes it easy to find the electric field for things that are highly symmetric. So a point charge, a sphere, or spherical shell. Now, those you might say, I already know how to do those with Coulomb's law. That's true, but this sort of makes the argument for why they behave nicely as point charges. For lines and cylinders, a little bit different, and then an infinite plane of charge. So we're going to look at all those. Gauss's law is written like this, which is maybe a little bit strange looking. That integral symbol with the circle around it means it's a closed integral. Basically, you're integrating over an entirety of something. In this case, it's a surface integral. It could represent a line integral, but that's what we're dealing with here. This dot dA is an area vector. We'll talk about the specifics of all of this. And Q over epsilon naught is the specific amount of charge enclosed by this thing we call a Gaussian surface. But we need to know what a Gaussian surface is. How do we define that area vector dA? And then this thing called electric flux, which is really the integral of E dot dA, is what we're looking at there as we go. So a Gaussian surface is not really there. It's an imaginary surface you create in your mind that you're using to help you understand what's going on in the world to look at the electric field in the case of Gauss's law. You can sketch it to use your problem. It could be any shape, but it must be closed. It can't have any holes in it. It can't be a box that's open on one side. It has to be a closed box. Some are really good for problem solving, things that are like a ball or a sphere or a can, like a cylinder or a box. Things that are irregularly shaped, like a potato, they technically work, but they're hard to use to solve. And our focus here is really picking a Gaussian surface that allows us to solve the problem simply. That's what we're going to be all about here. So for example, this box, which is a rectangular solid, and this cylindrical solid here, we can think of those as Gaussian surfaces. Now, when it comes to the area vector, in something simple like a cylinder or a box like this, the area of each side, or the lateral surface area plus the area of the two end caps for the cylinder, could be all we need to know, and we don't really need to do anything special to integrate those. The area vector is always perpendicular to the plane and pointing outward. So the area vector for the cylinder is sort of radially outward, and then for the two end caps are out the ends. That's how we define an area vector. It's a little bit confusing because the area vector is perpendicular to the surface, but if you think of it kind of the way the normal force behaves, that can probably help you understand it. If you have something a little bit more irregular, something that curves, we use dA, the tiniest little bit of area, right? That differential kind of view is always in thinking of it as arbitrarily small. So you could fit basically an infinite number of them on any given object. We don't really want to use those irregular surfaces for Gauss's law because they're harder to use, but that's the concept behind it. The other interesting piece, kind of the third piece that we need in order to solve a problem like this and understand the electric field, is to talk about electric flux, which in this case you get the symbol phi sub E. We'll also get one for magnetic flux in a little bit. But it's basically flux is flow through a surface area. So if you think of taking like a ring of just masking tape or something and holding it up and letting water from a faucet run through it, the amount of water going through a particular area is a way of thinking of flux. And so if you imagine, there are a couple different ways you could increase or decrease the flux or flow, right? You could turn up the water or turn down the water, right? Make it so that there's a lot more water running or a lot less water running would be one method. Another method would be to change the size of the ring, right? If you have a really little ring, only some water would go through it. If you have a really big one, more would. And so what we do to define flux is we talk about the electric field lines, and we sort of say how many electric field lines are going through a given area. And that's what we mean by flux. Now, this could be water, it could be air, right? If you think of an air vent, air coming through it. We define electric flux in this way, as the integral of E dot dA. And of course, the dot product means that it's the electric field strength times the area that you're going through times the cosine of theta. And that is the angle between the electric field vector and the area vector. When they're both in the same direction, right, obviously we get our maximum for cosine. Flux is maximum when E and A are parallel, so theta is 0. And so what we do is we say, well, for simple cases, the flux, the integral, is just the electric field strength times the area, if we have a simple situation. It's also good to notice that you can have zero flux, right? If these are dots pointing out of the page, that's the electric field coming out at you or out of the screen. And the area vector is perpendicular to that, so you get zero flux. Now, when we're talking about flux, positive and negative flux depends on whether the electric field lines are going into or out of. And so here we have some electric field lines going across the screen, and we have a cube. Now, a cube has an area vector in every single dimension, positive, negative, x, y, and z. And so depending on where the electric field is going relative to these area vectors, we get different amounts of flux or different signs of flux. For all the sides, right, that are sort of pointing out at me or straight up or into the page or down, there's zero flux, right? For A1 and A2, A1 is going to have a negative flux because the two vectors are opposite each other, and A2 is going to have a positive flux because they're in the same direction. We can also deal with the angle piece, right? The flux through a square surface with sides of 10 centimeters, that's area of 10 centimeters times 10 centimeters or 100 square centimeters, we would probably do that in meters, is placed at this 30-degree angle. And so what we're interested in is this flux. Well, it's side squared, the area, times the electric field strength, times the cosine of the angle. And this is lifted up at a 30-degree angle, which means the angle between the electric field and the area is 60 degrees. That gives us an answer, looks like that, 2 Newton meters squared per Coulomb, which the unit, I will say, is not the most intuitive unit. I mean, it comes out just fine. It's newtons per Coulomb, which is electric field, and then area, which is meters squared, but not necessarily a pretty unit and easy to remember. So how do we use this? Well, if you take a Gaussian cylinder, right, like which has, a particular radius r, placed in a uniform electric field parallel to the cylinder axis, you'll notice that the lateral surface area, the dA for the side of the cylinder or the side of the can, is going to always be pointing perpendicular to the electric field. This is a very good Gaussian surface for a uniform electric field going across the page, because we only have two discrete areas that we have to worry about. dA that is pointing to the left and dA pointing to the right. And so the flux is positive at the right end cap and negative at the left end cap. And it's 0 through the curved surface because of the perpendicular. And if we have a positive amount plus a negative amount, same magnitude, and then we have the 0. So we end up with 0 net flux, which is pretty nice. And so because of that, we can start to use Gauss's law, right? And so when it comes to Gauss's law, what we really care about is net flux, the total flux in and out added up for a system. And that's why we add that little circle. This is a closed surface all the way around. We're going to look at the flux in and out. The in is negative, the out is positive. We're going to add those up, and whatever the total is will be our flux for our system. So the net flux on this Gaussian cube, 10 centimeters on the side, in a uniform 400 Newton per Coulomb electric field, what is the flux? Well, for something like a cube, we basically take the 6 sides and we do the calculations for each of them. We have 2 sides that have a flux, one positive, one negative, and the rest of the 4 sides have 0 flux. But because this is a uniform field, the same amount of flux in and out, same positive and negative, ends up being 0 total. If we tilt the cube, does the net flux change? It does not. It becomes harder to calculate because now every side has some flux, positive and negative, and we need to deal with all these angles. But visually, if you see, every line that goes in of electric field also comes out. And that is kind of what we want to see. That for a closed surface in this uniform electric field, the same amount of flux goes in and out, which is very nice. Every field line that flows in flows out. And that means our net flux is going to be zero. So how would we get a Gaussian surface with a net flux that is non-zero? You might say, well, that causes problems, so why would I even want to do it? Well, the reason we want to know is because if it doesn't, then Gauss's law doesn't really tell us anything. But if you put some charge inside, it's easy to get this, right? We know that electric field lines behave in such a way that they go out from positives and into negatives. And if you put a charge inside a Gaussian surface, a single charge, then certainly there will be electric field lines going out of it or into it, depending on its sign, whether it's positive or negative, right? So we get to now the definition of Gauss's law that says the net flux for any Gaussian surface is equal to however much charge is inside. Charge enclosed is how we'd say this. How much charge you've sort of trapped inside the surface divided by epsilon naught. And epsilon naught, of course, is a constant, right? This assumes we're in a vacuum or basically in the air. In different materials, these numbers change. And we'll talk a little bit about that later on in the year as we get closer to the end. So here's the summary. If no charge is enclosed, then no E field lines start or end inside. So the flow in must be equal to the flow out. So the net flux is zero. If the opposite is true, then there will be a net flux, right? So that's it. That's the fundamental ideas here. We will talk more about how we use Gauss's law then to actually calculate the electric field in a variety of situations in our next video.